Hello everyone. So today we are going to let you know about EMF equation of DC machine. We have already covered basic construction, introduction, classification, working principle and basic laws of DC machine. So today we are going to talk about EMF equation of DC machine. So in this we will discuss about several factors, and the most common one is, as we know, the second law of electromagnetic induction by Faraday is whenever a magnetic flux is changing a conductor or a linking with a conductor changes, an EMF is induced, and that EMF is directly proportional to rate of change of current of magnetic flux in unit time. We can write as so. If I'll just say this is a 4-pole DC machine. This is a rotor. Suppose these are conductors. We are just letting 4 conductors. This is the flux. So now we can think that the EMF of a DC machine depends on number of poles. We will define number of poles by P. The second one is the speed of rotation, like how many times the conductors cut the flux. That depends on speed of rotation, and we take speed of rotation in rpm as n, but we have to find the speed in 1 second. So a minute have 60 seconds, so the speed, or I'll say the time taken to complete one rotation, will be n upon the number of rotations made in a second are n upon 60, and time taken to complete one rotation is 60 upon n. This is time. So we combine these all. EMF is equal to P poles 5 flux upon T, which we have find out equals to 60 upon n. 60 upon n. This n shift to here, it will become P phi n upon 60. Now the concept that comes is parallel path and conductors. Suppose there are z number of conductors. A slot can have many conductors, but a turn have 2 conductors. One turn two conductors. Say this is one turn, one conductor, second conductor. So, and the winding is so designed that particular conductors come into a separate parallel path that is defined by A. So, the number of conductors per parallel path will define the number or the EMF induced per pole, per conductor, per parallel path. In a conductor per parallel path, that could be Z upon A. Here Z defines number of conductors and A defines number of parallel path. So the EMF equation we have at the end is phi Z and P upon 60A. And for a particular DC machine, number of parallel paths are constant, poles are constant, conductors are constant, and 60 is also constant. So the EMF is directly proportional to flux and speed. As the EMF increases, or say as the speed increases, the EMF increases. The flux increases, the EMF increases. We can do some numericals, like we have 20 slots, each slot shares 8 conductors, so there are 160 conductors. Say it is running on 1000 rpm with 0.07 farad of 0.07 Weber of flux, having 4 poles and lap winding. As we have discussed that in a lap winding, number of poles equals to number of parallel path, and for a wave winding, number of parallel path equals to 2. So it is lap wound, so put the values directly here. 0.07 into 1000 into Z is 160 into P equals to 4 upon 60 into, as for lap winding number of poles and number of parallel path are same, that number of parallel path will be 4. Cut that simply. That results to 75603. So the resultant is so the EMF induced will be 186.667 volt. This is how the things are done. From here, the numerical portion of DC machines have been started. We will discuss about various other numericals in the later chapters. Thank you for the day.